Okay, hello everyone. Mm, right, so people are still joining, but I think we can start. All right. So this is okay. So let me share my screen first. Okay, so this is the first among a series of workshops which we are doing, like from the electronics department junior staff, and the goal of these workshops is to familiarize students with tools and languages. So what if students to like later on, like when they learn the theories in the classroom, they can go and test them out in these tools. So we will be introducing certain ideas, so some digital design concepts and everything in a very loose sense. Later on, they will be taught rigorously in the classroom. So when you are taught in the classroom, you can go back and test it out using this language, using these tools. So that's the whole idea of it. So the first session, like as you know, it's on Systemverilog for digital design, simulation, and synthesis. And let's see. Okay, I'm Abarajithan, and you can contact me in this particular email address. And the code of this, like I'll be showing, and we will be doing everything. The code is available in this particular GitHub repository. So if you lag behind, or if you need to look at the code or something later on, you can always go to this one. Okay. And for this particular the sessions, the book I'm referring to is this one, RTL Modeling with Systemverilog for Simulation and Synthesis. So it's written by this person, Stuart Sutherland. So he was there in the Systemverilog committee for a long time, for I think since 1995 or something. So he's one of the people who developed the language, and he has written a book about on this particular subject. So for a deep understanding of the concepts, you can always go back and refer to that. All right. So I hope that you have installed the software. That is, yeah. So you have installed the software Xilinx Vivado, or else you can have any kind of similar software, which is Xilinx ISC. So that is used for older Xilinx FPGAs, or Ultra Quartus. So that is what used for the Intel Ultra FPGAs. So you can have one of those as well. And so if you know how to do synthesis and simulation. And why are we using 2018.2 here? Because University of Moratuwa has some certain licenses for which you can use for some advanced boards. So if you are a student of University of Moratuwa, you can always request a VPN access, and you can use them later on. So if you install it now, you'll be able to use it later on. All right. So I hope you have installed the Webpack edition and it's ready. And if you open it, it should look like this. Okay. Right. So the text editor, it's not important. Like you can use anything. The Vivado, it has its own editor. I'll be using VS Code. And okay, the knowledge it's not nothing much is needed. If you know about multiplexers and say logic gates and stuff, you should be able to follow. All right. So right. So some overall idea, like what are we doing? So first of all, there's a wide range of participants here. So let's go to this. Yeah, so these are the responses. About 190 people have joined, like registered, and more than half of them, the people are still registering. So more than half of them are new to this. So in that case, I'll be focusing a little bit more on the basics, on the very first few examples. All right. And there are people who have done it before and lost touch, as well as the ones who are familiar with Verilog. So that's because in University of Moratuwa, we teach Verilog as the language. All right. And there are VHDL people as well. All right. Then okay. So most people are from our batches, 17 batch, 16 batch, and 18 batch. All right. However, there are these some people who are from what A levels as well. So I don't know. Like I think somebody might have given the link to them. So to be honest, this might be a little bit advanced for A level students. However, like if you are really interested and if you can follow through, then no problem. Like you are welcome to join. All right. Okay. So right. So there's a big range of participants. So in the first few slides, we'll be talking about HDLs. So HDLs are hardware description languages. So Systemverilog is a hardware description language, and we'll be talking about them as well as FPGAs, what is synthesis, what is verification, some. All right. So yeah, so we'll be recording this and we'll be sharing the recorded one publicly. So if you're unable to attend or if you want to leave in the middle, so it's not a problem. So you can go ahead and join. Okay, but before you go, give us feedback. Okay, so go to this place and give us feedback. I'll be showing. All right. So what are we going to do? We are going to implement 7 digital circuits. So of increasing complexity. So like first we'll be starting with a 1-bit full ladder. So just logic gates, some AND gates and XOR gates and everything. So from there, like we will put n number of them together. Then we'll do a ALU, that is an arithmetic logic unit. So which is inside the processor. Okay. So yeah. So it's inside the processor. So we have an ALU, arithmetic logic unit, which does the calculations, the addition, subtraction, multiplication, and everything. So we'll be implementing the simplest version of that. Okay, with arithmetic operators in Systemverilog. Then we'll do a simple counter, a circuit that keeps counting. So which is like we use it quite a lot in real world examples. And then we'll be doing a parallel to serial converter. Okay. So if you look at this, the 1 to 4, the examples 1 to 4 are quite simple. So it is for the beginners as well as for the people who know other languages to introduce the features in Systemverilog. Okay. So I'll be using different syntax styles of Systemverilog in every example. So you can see like how things are done. Okay. From 5, 5, 6, 7, the examples are a little bit advanced. So that is a parallel to serial converter. So this is there in your say USB bus or else any kind of serial bus. So that is like a UART. So in any of them, you have a parallel to serial converter, and we'll be implementing a simplest version of that. And there I will be introducing the concept of state machines. Then we will do another ALU, the same ALU, arithmetic logic unit, but this time using IP cores. So that is IP cores are some circuits designed by somebody else, and they are available to us. So we'll be using them and making an arithmetic logic unit. And finally, we'll be building a matrix multiplier. So that's a little bit advanced example. All right. So basically, you will be doing this. So the code will be shown in the slides. It's available in the slides as well as available in GitHub. So what you will do is you will type this code from the slides in your machine, and you will be like synthesizing them. You will be simulating them, and you will get a feel of how to do these things. All right. So yes, and yeah. So I have checked all the codes. Okay. So I have checked all the codes, and these are yeah. So I have checked all the codes, and they are working. So like if you copy the codes, if you type the codes from the screen, like without any mistakes, without any typos, they should work as it is. However, we usually make typos, so there will be errors. I will be showing one example of how to fix the errors. But because there are like 191 people, my goodness. Okay. So because there are 191 people, like I won't be able to check each and everyone's screen and resolve the errors one by one. Okay. So ideally, this kind of workshop is done in a lab where there are a lot of instructors looking at the screens and like helping you out. But unfortunately, because of COVID and all, and we are doing it in Zoom, and I'm the only person doing this, so I can't look at everybody's screen. So what you can do is like if you have an error, so I check the codes. If you take the code from the slide and put it as it is, there won't be a problem. But in case you come up with an error that you're unable to solve, what you can do is you can ask me a question, or else you can contact me after the session, right? And the full working codes are available in GitHub. So after the session, you can get that code and you can put it and run, all right, and implement it, and before coming to the next session, so you can learn like that. All right. So okay, other thing is keep these slides open, all right? So because what I sometimes I might move back and forth and everything, so keep the slides open if you are like when copying down the codes. So like it will look something like this if you yeah. So if you go to that particular link, it will look something like this. So you can open that in you don't need PowerPoint. You can open that in web browser and you can go through the slides. All right. So okay, so this is the link, and but you may take notes. So you can keep a small book and write down the certain syntax, so like any important points. Okay, and keep asking questions. So this is very important. So just follow this link, and you'll go to this something called the Slido. It looks like this. Yeah, so it looks like this. So go there, and the first thing is you can give feedback. Okay, so over here you can type your feedback, okay, something, and send. All right, or else what you can at any time you can keep asking questions here. Okay, so like you can type any particular session. So what is Systemverilog? Okay, oh, what do I mean by verification? Okay, so these kind of questions. So these are questions I gave, and you can if you like, if somebody else has asked the question you can upvote this, you can press this. Okay, right. So you can do all that, and I will be taking questions. Okay, so I will answer the questions while others are implementing the circuits. Okay, so while they are looking at the slides and implementing the circuits, I will go through the question and answer them. And before you leave, give feedback. All right, go to this particular link. That is the same link as here. Okay, go to pulse and feedback. Okay, here type something and give. Okay, so if you are leaving in the middle or like at the end of each session, don't forget to give feedback. So we need it for the other sessions as well as to improve this in the next session. Okay, right, good. So you can check the okay. So the thing is like now these slides are designed to be self-contained. So the idea is like there are certain slides with Vivado videos. Okay, how to create a project in Vivado, how to create IPs in Vivado. So how to do synthesis, how to do simulation. So in Vivado. So those are given as videos in certain slides. So I will not go through them because I will show you like by myself. Okay, but in case you missed that, so in case like what after I showed you, like you have a doubt and you want to go back, you can always go back to the videos and check them out. All right, and in GitHub you have the code. Okay, so that's how we are doing this. Let's go to start. All right, so keep asking questions. Great. So like the first question is, what is an HDL and why does it exist? So more than half the people like are new to this. So like let me go through it quickly. So HDL is hardware description language. Okay, so the idea is this. Now this is a diagram that I have taken from Atmel's Atmega 328P datasheet. So what is this? This is the chip you find in Arduino. Okay, so it's the IC you find in Arduino, and from the datasheet I have taken the diagram, and this is what this is how the IC works. So what is inside the IC? So what you see here are like basically this is a multiplexer. Okay, that's a comparator, and yeah. So you have this is basically and this is a data bus. Okay, so this is basically a digital circuit. Okay, so not only this. So all processors, GPUs, and ASICs. So ASICs is application specific ICs. So for example, like all the mm, right. So for an example, this like any kind of digital chip you find is a digital circuit. So it has all these multiplexers and these kind of things inside. Okay. So what are digital circuits? They are made in silicon, fabricated in silicon, and silicon is doped to form transistors. Okay. And transistors together form gates, logic gates, and logic gates together form multiplexers and registers and everything. Okay. So these multiplexers implemented as a bunch of logic gates, and the logic gates are implemented as transistors in actual silicon, right? So what we do is like when you design these things, like it's quite difficult to go to the transistor level and design all the transistors. Okay. So what we do is we design these things in something called the RTL level, RTL. So the register transfer level. So in register transfer level, we will be describing these multiplexers, and we will be describing the registers and everything, how they are connected and all. And then there's a software like so something like UARDO. So that software will take your description and it will turn that into an actual circuit. Okay. So now in the language that we use to describe this digital circuit as a text file, okay, that is called an HDL. So what the Systemverilog is one of those. So one main objective of Systemverilog is hardware description. That is, you describe a circuit. This circuit you describe as a text file. So that is what this language is all about. All right. Then it also has another purpose, that is verification. So verification means testing in simulation. Okay. So we need a language to write tests and simulate the functionality. So to make sure the circuit does what we want. So Systemverilog does both. Okay, so you can do this as well as this using the same language using Systemverilog. All right, so that is a hardware description language. Okay, so all right. So let's say you have a digital circuit. Okay, say you come up with a digital circuit, you design it. How are you going to implement it? So first, what we do is we take the specification from the customer or from somebody, and we design a design, and then we do simulation and change the design and simulate it again. Keep doing it until the whole thing is correct, until we verify it. Okay. So throughout these sessions, I will be only focusing on these two things, RTL design and simulation, nothing else. Okay. Then after you do that, you can either go for an ASIC. ASIC is a digital chip. So this is bare blank silicon. Okay. So it is just a silicon. In there, you can build your own chip. You can put your own designs and build it. So you can go for that. But the problem is, like, only if you have high volume, it is cheaper. So if you have low volume, if you want to make 100 chips or like 50 chips or something, it's very expensive, ASIC. But on the other hand, it has better performance because that silicon will have only the logic you need, only the multiplexers, only this one you need. So then it will be like very fast as well as like very cheap. Like it will be smaller. The chip will be smaller. But the development takes a long time. So the reason it takes a long time is that you have to be absolutely sure the circuit is working. Otherwise, you will spend millions of dollars, literally millions of dollars, and finally you will find out like it doesn't work at all. So you have to do this cycle again and again and again and again a long time until you finally verify it. So those are the, if you are going for ASIC. So if you are going for ASIC, how do you do this? You do something like this. So that is yeah. So once you finish this one, that is you design your circuit and it becomes a HDL code. You take the code and there are different tools, different softwares. Say what are the synopsis tools? So they take this one and do the synthesis. And synthesis means they take them and they translate your code into a different code. And in that code, you basically have flip-flops and you have AND gates and OR gates and everything, very primitive things. So it translates to that code, and then like there is another tool which does the place and route. Okay, so in a silicon chip, it will keep those things here and there, and it will put the wires inside and everything. So it does that design, place and route. It does all these things. After you finish everything, you send it to fabrication. So what is fabrication? So somewhere in Singapore or else in America or something, there will be a very clean lab. The people are wearing white clothes and everything, like a very clean lab. So inside there, they take these files and they make the chip in actual silicon. Okay, and it's a very expensive process. So that is a simplified IC design flow. You will learn more about this in semester 8. So in digital IC design module. Okay, the whole module is about this process. Okay, then like the thing we are using now, like mostly, like we will be using now is FPGAs. So what are FPGAs? FPGAs are field programmable gate arrays. So the idea is they are generic reconfigurable chip. That means it's like a flexible chip. So inside them, the connections can be changed. So there's one generic chip. You take the chip and you can put your digital circuit into that, and you can realize it. So yeah, how does it work? Inside that, it has lookup tables, like lots of thousands of lookup tables, as well as switches. And when you finish this code and when you send this code into the FPGA, it connects certain switches, and like the circuit you want gets created inside. All right. So you can quickly change the designs and iterate. That is the advantage in FPGA. So you don't have to like make sure it absolutely works. You can quickly put it there and see whether it works, then change it like that. And that's the advantage. But the problem is that silicon has all this generic routing logic also. Okay, so as a result, it is not very like it is less performant than an ASIC. So ASIC is more performant because ASIC has only the logic you want. FPGA has some unnecessary logic that you don't need also, right? Then the advantage of FPGAs is cheaper in low volume. So let's say like you are making like say 1,000 or 10,000 chips. FPGAs are cheaper. If you are making say millions of chips, like if you are like making an iPhone or something, then ASIC is cheaper, right? So these are FPGAs are usually used in network routers, then signal processing applications, scientific instruments, oscilloscopes and all. Then inside video encoders and everything, satellites. So they use FPGAs. Okay. So we'll be using, okay. And the flow for FPGA is this one. That is you synthesize. So there's a tool in Vivado, you can do that. So Vivado does synthesis for FPGA. Vivado can do place and route for FPGA. And you can program the FPGA with bitstream. All this you can do with Xilinx Vivado, right? Or else you can ultra quarters, so whatever. Okay, now where to put your algorithm? So let's say like you have so these are some FAQs, frequently asked questions. So if you already have an algorithm, should you go for a CPU, GPU, or an FPGA, or an ASIC? Okay, so idea is like CPU, the difference between these is CPU has only few cores. Okay, so like say 3 or 4 cores, but they are powerful cores. So they can do a lot of things. So they are highly pipelined. They can do multiplication, like division, floating point operations. Like they can do 1,000 different things, and they are very powerful, but only few cores, and they are optimized for conditional code. So that is like if statement, if else statements and everything. It's optimized for that, and they are called single instruction, single data. So usually, and yeah. So then if you are implementing a complex operating system or something, then you can go for a CPU. For an example, there are these open source RISC CPUs. So like now ARM is one of the RISC CPUs. So you can put Linux in that. Okay. And I think in our university, they have put Linux into RISC-V also. So if you are doing some complex operating system, then you go for CPU. Or else if you are doing some specific task, say video encoding or decoding or something, then we usually do that we can do that in GPU. Okay. So the idea of GPU is there's like hundreds, so if not thousands of small tiny cores. Okay, so for example, CUDA cores, and each of them, they perform a simple computation. So they are not complex as this. They can't do many things. They can only do a few things, and everything are very simple. And what you do is the driver software for this one, it will take multiple of these chips and program them this way. That is single instructions, multiple data. So all of this, or most of this, will be doing the same thing, but on different data. Okay. So now this is very highly useful when you want to do like say video encoding or else gaming or something. So in gaming and everything, you have the same equations, right? So like Yeah. So to calculate the pixels for the screen, you have the same equations, you have the same computations, but you have to run it for like thousands of pixels. Okay. So in that case, the GPU can do everything in parallel, most of these in parallel. So as a result, GPU is more optimal, and especially ML training. So you have the same back propagation, same algorithm and everything, same equations, but you are doing it for like thousands of parameters or millions of parameters. So then GPU is good for that. Then where do you go for FPGAs? So FPGAs are a blank canvas. So now CPUs and GPUs, they have a fixed architecture. So like somebody has made an architecture and some of them are good, some of them are bad, not good. So like for you can select between different CPUs and everything. But FPGA is like a blank like canvas. So you have to design your own architecture. You have to come up with your own digital circuits for this. And the problem with FPGA is FPGAs are slower than CPUs and GPUs. So CPUs are like 2.9 gigahertz or something. GPUs are also around say 2.9 or 3 gigahertz or something clock speed. But FPGA has the maximum clock speed around say 400 megahertz or say 600 mega. I think even the best ones might have around 600 megahertz or something. So they are like definitely slower in clock frequency than CPU and GPU, right? But if you can design your digital circuit, which is very optimal, then you can beat CPU and GPU in speed. Okay, so the idea is like so FPGAs are like about 10 or 20 times slower, okay, than a CPU. But if you can make a digital design architecture which makes it what say 100 times faster, okay, than a CPU architecture, then definitely FPGA is going to be faster than CPU. All right, okay. Then so FPGA, where is it used? It's used in signal filtering, okay, in scientific instruments, so example. So things like that. Right. So yeah. So CPUs. Okay. So these are like more flexible, they say. So why is it flexible? Because you can easily change the code and upload. But in FPGA, you have to change the digital design. So that is, you have to change the circuit. It takes some time, and it's harder than that. And efficiency, the ASIC is more efficient. FPGA is second, GPU is this one, like that. Then cost per unit, ASICs are much cheaper. If you are making millions of copies, like a million ASICs are cheaper than a million CPUs. Okay, so that's the idea. All right. So I think now you have some understanding of like what HDLs are and what digital circuits are and why do we use them and everything. So a quick overview for the people who are coming from VHDL and Verilog backgrounds. All right. So that is a tale of three HDLs. Okay. So the first HDL was made in 1952, and in 1974 there were over 50 HDLs available. Okay. So 50 different languages to do the same thing, to describe digital circuits. So then what happened was like around in 1987, yeah. So the US Department of Defense, they started a particular project. That is a very high speed integrated circuit project. It was a huge project. So for that one, they funded two companies, IBM and TI. And then they found, okay, like there are too many HDLs in the market. So what they did was like they gave money and resource and everything to develop a new HDL. So that's a standard. Okay, so which the entire America can use. So then they came up with these two companies came up with VHDL. Okay, so the meaning of VHDL is this one. Okay, very high speed integrated circuit hardware description language. All right, and it's a very strongly typed language, and it's verbose. So I haven't done this design, but I have seen some. So like you have to write a lot of code to get something done, but on the other hand, you tend to make less mistakes. And right now, VHDL is being used only in the old designs. So the reference is this one. So like you can go and check this out. So it is a paper presented at Synopsys. So in there, like they say today, the VHDL code, there is very few VHDL code being written as new ones. So most of the code is like very old, like designs like from 20 or 30 years ago, which they are still maintaining by changing it here and there. Other than that, like they are not writing any new code, not in Europe, not in America. All right. So the language is kind of dying. So over here you can see, all right. So then what happened? Like in 1995, like another company came up with a language called Verilog. So even before 1995, they had this, and in 1995 they made it into an IEEE standard. Okay, so yeah, so Verilog is kind of less verbose than VHDL. So you don't have to write too much. You can write with less code. You can represent the circuit, but then it's kind of weakly typed. So it has you can have some errors. So you can make mistakes. So for an example, like when you can assign different, like two wires of different sizes, it doesn't give an error. It automatically does that. But because of that, you might make some errors. So those problems are there. Then yeah. However, Verilog is much easier to learn and to work with. And later, like it was acquired by Cadence, and then now it has evolved into Systemverilog. So Systemverilog, it was started in 2000, around 2002 or 3 or something. So the idea is like now, so even Verilog was kind of too old, so it doesn't have certain features. So what they did was like what they introduced new features to Verilog and created a new language called Systemverilog, right? So Systemverilog is a superset of Verilog. So that's like you can take an existing Verilog code, you can just change the extension to SV, Systemverilog, and you can put it into anything, it will work. Okay, so because like Systemverilog is a superset of Verilog, and Verilog was discontinued, and this replaced as the IEEE standard in 2012. So now Verilog is not the standard anymore. So Systemverilog is the standard, and companies like Synopsys and like the EDA companies are advocating for Systemverilog. Okay, so it is a nice skill to have. All right, and all the major tools, they support Systemverilog now. Okay, so other than that, say one last thing, that is HLS. So this is high level synthesis. Yeah, so these Xilinx, they have come up with something new, that is you can use C or C++ to develop hardware directly. So you don't have to sit and write an entire circuit. Okay, so you can write a C code, and you can tell, okay, pipeline here, put a pipeline there, then you do this in parallel, you do that in series, you tell those, and then it will make the circuit for you. But what is the problem? Problem is you don't know what's happening behind the scenes most of the time. So you can't control every clock cycle, so you lose that control. But certain designs you can develop very fast. So that is the advantage of this one. Okay, so we are looking at Systemverilog now, right? Okay, so now first thing for the beginners, and like even people who are experienced with this, like have this problem that Systemverilog is not a programming language. Okay, so like so if you read it like a programming language, you will make a lot of errors. So when you write the code and everything, the design thinking. Okay, so how is this different? Let's see. So look at this one. So this is Python. Okay, so like it's a programming language, and see what happens here. So in a programming language, we execute the code from top to bottom, right? So basically the computer or else a processor is reading the code from line by line, and it's doing, okay, it does this line, this line, this line, this line, and like that. So we call that control flow. Okay, so we say there's something called a control, and that is flowing through the code in a certain way. Okay, so I have represented the control by this yellow dot, and let's see what happens. Okay, so first, when you run this code, this line, this line, this line get executed, and now you're asking to print C. So what will you get? Okay, so think about it for a moment. You are assigning true to A, false to B, and A and B to C, and you are asking to print C. So it's going to be what? It's going to be false. Why? So A is true, B is false, A and B is false. Right. Now, you like, let's say you execute further. So now you change A. So A is true, and you change B. B is also true. Now you ask to print C, what are you going to get? You will still get false. Why? Because what so C, what is C? C is a variable. A variable is a memory location, a place in the memory where At this point, you take an AND between A and B, and you have written into the memory location. Okay, and that is why you write as false. And you did not update C after that over here. Okay, you didn't change the memory location after that. So because of that, when you print it again, also you get the same thing as here. Okay, so you can see that this code is going sequentially, one line after the other line after the other line. Okay, right. So what is this one? This for loop, and we are doing say 3. Okay, and S1 is 0. Then we are adding 1, adding 1, and adding 1. So what are we going to get? And we are printing that. We'll be getting something like this: 1, 2, and 3. And here it's the same. Okay, so when it goes here, it comes out of that loop and it does not update it anymore. So you have only 3 values printed. Then you go into this and you have what? You print 1 and 2. Okay, so first this runs, then this runs. Okay, then after doing all this, this control has exited the program. Okay, so when you start a program, the control goes into the program, it runs like this, it goes into these things, executes them, then comes out. So at every line, it executes that line. Okay, so that is a programming language. What happens in Systemverilog or HDL? So hardware description language is something like this. So here, what we are doing is, this is not a programming language. This is, we are describing a circuit. So this is a circuit, and the circuit we are describing is, we have A and B, we take an AND and send it to C. Then there is something called S1 and S2 are 2 counters, and we have given the clock signal there. Every clock signal, we are counting it by 1. Okay, 1, 2, 3, 4, like that, we are incrementing it by 1. Okay, and giving the output. Right. So this example, like it's a, if you don't understand it, like don't worry, because we'll be looking at this later. Okay, so we write the code like this. Okay, and we do the simulation like this. Now the thing I want you to note here is, like, you see, look at this. Okay, so here we are changing. Okay, these are different times, 0 different time. Okay, so first we have A is 1 and B is 1. So C is 1, A and B is 1. A is 0 and B is 1. C becomes 0. Okay, immediately. Then like A is 1 and B is 1. C is again 1. So what happens? This line, okay, at the same time, this one is incrementing. This one is incrementing. And this one is also incrementing. See, S1 becomes 0, 1, 2, 3, 4. S2 becomes 0, 1, 2, 3, 4. So this line, and this line, all 3 are happening at the same time. Okay, so it doesn't go through there and do this, finish it completely, comes to this one, come to this one. No, it's not a programming language. This is a circuit. Okay, so in a circuit, these things are happening simultaneously. Why? Because in a circuit, you put these things together and the signals flow through everything in the same time. All right, so if you want to take one thing from this session, it will be this one. Okay, so it's not a programming language. Okay, so whenever you are writing code, whenever you are writing hardware code, like there are if statements and everything, don't think of it as a programming language. So that is where a lot of people make mistakes. So always think of what is the circuit you want to make, then think of how to create the circuit in the language. Okay, so okay, then all right, so right, so this is just a summary of what I said. So that is like a programming language step by step instructs a processor. So you already have a processor, you tell step by step what to do. Hardware description language, it describes a digital circuit as a text file. Okay, completely new. And you can design your own processor. So that is like in semester 5, like we have a project, so where we design our own processor and we can make it execute a programming language that we create. Yeah, so we can design our own processor and make it to execute a language we created. Okay, our own language. So you'll be doing that in semester 5. Then like a programming language has control flow. Control goes like that. HDL, it basically tells a synthesis tool how to make a circuit. Okay, so it's called data flow. So that is like after the implementation, the data are flowing in the same time. So that's called data flow, right? So then a programming language is compiled. So that is, it's translated to a low level code which the processor can understand. hardware description language is like we call compiling, but it's actually synthesis. So it translates your design to low level. What? Yeah. Okay. So low level target specific language in the net list. Right. So right. So once again, all right. So now another aspect of the Verilog, like Systemverilog, is it has two objectives. Okay, so this is where a lot of people get confused. Like even people who have some experience, that is like which part of Verilog is synthesizable and which part is not synthesizable. Okay, so some people have this question all the time. So the answer is this one. So the Systemverilog and Verilog, they are languages with two objectives. Okay, one language that does two things. So one is hardware description, which we just talked about, and this is the same circuit. Okay, and the idea is like you do this one, you write this one, and it is called the RTL design. RTL is register transfer level design. So you make this module like this, and you synthesize, and when you synthesize, you get a circuit like this. Okay, so I got this from Vivado. We will see how to do this. And after doing that, we do verification. That is simulation. So in simulation, you check whether how this if your circuit is working properly. So we'll be looking at that also. So how do you do that? That is, we write this something called a test bench module, and in the test bench module, we will be telling, okay, like create a clock cycle. Okay, so now this part of the code is doing a clock cycle. So it's giving the clock is rising, falling, rising, falling, and everything. Every half a clock cycle, it's changing. Okay, right. Then afterwards, here what we are doing is we are like creating okay, every positive edge clock, we are changing A and B. So at this point, we give A and B is 1. A is 1, B is 1. Here A is 0, B is 1. A is 1, B is 1. Okay, so we do all that. So yeah, so this is a verification. Okay, now like this part of the code, that is delay. Okay, this one. Okay, this one, some kind of delay or else a positive clock are not synthesizable. You can't put that in a circuit, actual circuit, but you use that to check whether your circuit is working. Okay, so like only in the simulation code you do that. You don't put it in the RTL or hardware description code. Okay, however, this one always FF at percentage clock. So this is synthesizable. Why? Because it creates a flip-flop inside. So we'll be looking at it later. Okay, so anyway, so the idea is like if you have this confusion, the answer is simple. That is, think about the circuit all the time. Think about the digital circuit. So you are writing the digital circuit as a language. Okay, so if you put a delay into here, then there is no way you can do that in a digital circuit, right? So like you can't ask a digital circuit to wait for 10 nanoseconds. Okay, so that is not synthesizable. So we do that only in simulation. So after 10 nanoseconds, we give something to check whether it's working, but you can't do that in RTL design. Okay, so always think in terms of circuit and implement it, right? So this is this one, the summary of that. Okay, so these are like okay, right. So these are some these are these videos. Okay, so creating projects and everything. I'll be showing you here. If you missed that, come back and look at this video at your own pace. All right. So I hope you guys have opened. Yeah. So people who haven't opened Vivado, please open it. Okay. So we'll be looking at how to create a project. Okay, and the project directory structure. Then after that, like we'll go on to make our first circuit. Okay. So All right. So keep asking questions. So if I'm too fast or too slow, if you don't understand a particular part or something, you ask questions. Okay. Somebody has asked me like he has a problem installing Vivado and how can I install it? All right. So can you? So that person, please contact me after the session. So in the first session, we will be yeah. So we'll try to do some examples. Okay. Then contact me after the session. I will help you with that. Then after that, you can implement the examples we did in this session. Okay. So I hope you have opened Vivado. It takes some time. And if you have opened it, you will get a screen like this. Okay. Right. Okay. So first thing, we create a project. Right. So before that, what we do is we'll go to some okay. You create some directory. Okay. So for an example, in my case, okay, so I think there's someone from India. I don't understand Hindi. Okay, like if you have any questions, please ask in English, Sinhala or Tamil. Okay, thank you. Right. So okay. So create yeah. So in like create a folder that is say Systemverilog, and we are going to keep everything inside this folder. First thing, let's create a folder called src. So we are going to keep all our Verilog files and Systemverilog files inside here. Okay. Then we create another folder called projects, and all the Vivado projects we will put inside here. And the reason we keep it separate is the reason is like we will have to delete these projects time to time, and we have to rebuild it and everything. Okay. So to make sure we don't accidentally delete the code, we keep it separate. All right. Okay. So create these two. Okay. Then once you create that, once you create that, go and create a project in Vivado. Click this. Okay. And it opens a wizard to create a new Vivado project. Okay. So what is a Vivado project? So it's basically like hundreds of different files, which helps you to do everything you do in Vivado. Okay, the simulation, say synthesis, and like synthesis results and everything, it will create as a separate file. So you will have like 100, 200 small files, everything. It will be arranged in a particular way. So that is called a Vivado project. Okay. So go to the next one. And yeah. So over here, select your location. Okay. So inside my inside the folder I created, okay, I have put I select the projects folder. Okay, and I give a project name. You can give project 1 or something SV, right? So you can see this like this. Okay, one important thing, that is like if you are using Windows, okay, don't put this thing, don't put this folder somewhere deep inside. Okay, so we made this mistake in the beginning. So like there is somewhere inside the work and inside D, inside something, inside something, inside something, inside something like that. Don't put it very deep. Reason is Verilog has a problem. Sorry, Vivado has a problem. It can't. But this the path of these certain things, it has to be short, not very big. So put it somewhere outside. Okay, maybe in your like in directly in D, create a folder and put it there. Also, I have put that in desktop. Okay, or somewhere. All right, and keep the name short. The project name like say only a few letters. Don't put too long, because like Vivado will be creating files called the project name dot project name dot project name dot project name. So after sometimes it gives an error. So keep everything short and small, something like this. Okay. So once you do that, go to next. And okay. So like take the default option, RTL project, don't specify sources. Next. Okay. Over here, we will be selecting the board, the FPGA board. So now we are doing this for FPGA, not for ASIC. And like we'll be selecting a board that is right. So from here you can select any Xilinx board you want. I will choose a generic one. So that is I will choose 702. Okay. So just search 702 and you will get like 2 examples. And over there, like select this one. All right. All right. So there is somebody. Okay, she doesn't understand anything. Like, can you ask some specific question in the Slido? Okay, use this one. Okay. So ask the specific questions over there, and let me know like if I'm too fast. All right. So because I'm not, like, I don't know whether you can follow it or not. Okay. So I will try to go kind of slowly, but let me know if I'm like too fast or too slow. So send me the messages over there. Okay. Right. So select this one. Next. 702 does not show. All right. So yeah, don't search here. Not here. Okay. Go to the boards and search here. 702. Okay. Select this one. Or else you can choose anything at all. Like it doesn't matter. Okay. So I can slow a bit. All right. So I will slow down a little bit. Okay. Yeah, he has found it. So basically select this one from the boards. Okay. Okay. So the difference between parts and boards is parts means FPGA chips. Okay. So sometimes what we do is like we take a FPGA chip and make a PCB out of it. So that's how you make satellites and all. You don't put a development board in a satellite. Okay. So you take the FPGA chip and make a PCB and then like put that PCB in the satellite. So in that case, what we do is we go to this parts, and from here you can, these are chips, particular FPGA chips. You take that and you can done all this one and do it. And okay, what is the project type? RTL. Okay. Then after that, choose 702. Okay, this one. All right. So I hope she has got it. And okay, so if you lag behind or like if you miss something, go to the videos in the PowerPoint slides. Okay, I have the same thing over there. See, so I have recorded this as a video as well, so you can follow it over there. Okay, you can create a project and you can add files and everything, right? Okay, then select okay, so finish. Okay. So you have created the project, and like we will be creating the files. Okay. So we will create the files and we'll put the files inside here. So for an example, you can see here. Okay. So these are the files I have created already. Okay. And so we'll put stuff inside here like this, and then we will be adding those files into the project. Okay. Right. Then let's do, okay, into the project. So you can open the project folder and see, okay, like these are all the different files it created. Right. So then let's move on. Okay. So I hope you have done that thing. And now we are doing the first design. Okay. So we have 7 examples. In the 7 example, we are doing the first example now. That is 1-bit full adder. Okay. So what is an adder? So you don't need to know the exact details. Okay. So you'll be learning that in the formal class. So the idea is like a 1-bit full adder is basically it adds 2 bits. Okay, so it adds 1 bit A and 1 bit B, and it gives out a sum as well as it gives out a carry out. Okay, and a C in and gives a carry out. Okay, so yeah, how does it work? Yes. So okay, I will answer these questions once you implement the circuits. Okay, right. So what we have is okay, a full ladder. So how a full ladder works is like it's just this. So you have a bunch of AND gates, OR gates, and XOR gates connected in a specific way. So let's say you have designed this full ladder. Okay, so somehow, and after designing it, how to implement it in circuit. So that's what we are going to look at here. So we are not talking about how to design this thing. So how to implement it in Systemverilog. Okay. So this is the code. Okay. So what you do is like create a file and type this code inside. Okay. So for example, okay. So I'm using Visual Studio Code. In their file open folder, desktop, Systemverilog, SRC, Systemverilog, this one, select. Okay, I can see the files in here. Create a new file. Okay. Okay, now look at this. Okay, so create a new file and we are going to type this one over there. All right. So save this as, okay. So save this file as, use this name. So it is like a standard practice. We use the same name of the module as a file name. Okay. So use full adder.sv. So you can use anything like say notepad or whatever. Okay. And full adder.sv and save it. Okay. So now we have created our first Systemverilog file. Over here, you can start typing this code. Okay. So like okay. So like this, type this code over there, and I will give you some time. So like I'm not sure how much time you need. Okay, I'll give you about 10-15 minutes. Okay, about 10 minutes. So type this code over there and save this file as like this inside SRC. Okay. So what you have here is now, okay. So before you start, look at this part. That is, what have we done here? Okay. So, right. So what have we done here? The idea is like this code describes this particular circuit. Okay. So over here we have input A, input B. Okay. So these are this A and B, these wires. This wire and this wire is represented by these two lines. Then input C in, output sum, this one, output C out, this one. Okay, so input A, B, C in, output sum and output C out. Then we have this logic wire 1, wire 2, wire 3. Okay, so they are these wires, this wire and this wire and this wire, wire 1, wire 2, wire 3. Okay, right. Now after defining all the wires, so now we are declaring the wires. After that we are going to connect the wires in a way we want. So first way is we are going to have wire 1, this one is equal to this wire XOR with this wire, right? A XOR with B is equal to this one, wire 1. So we say assign wire 1 equals A XOR B. All right. So okay. So what do you mean by the keyword logic? So the wires in particular, okay, I will give a loose definition now. I will give the exact definition later. Okay, so there's a slide called data types. I will give it over there. The loose definition is the logic represents a wire or a register. Okay, so both wires and registers are what are represented by logic. So if you want to create a wire, you just say logic wire 1. Okay, right. So do we need VS Code for that? No, you can do with like Notepad or whatever you want. Okay, and even inside here you have a okay, even in Vivado you can do this. So like, let me show you how. Okay, right. So click here. That is if you are not using VS Code, if you are using only Vivado, then what you can do is you can add sources, create design sources or something, or else wait, add sources, then design sources. Yeah, next add files. Okay, so you have to add this file into there anyway, whether you are using VS Code or not. You have to add that file. Finish. Okay, so now that file has been added as a design source over here. Okay, now this file you can edit it either in VS Code here, or else you can edit it in Vivado here. So you double click it, or else you right click and say edit. No, just double click it. You will open this one. You can type your own code here and you can say save file. Okay, so input logic A. Okay, and you can control S or else B, and you can right click save. Right, and it will keep on updating. Okay, so do that. Okay, so look at the slides and do that now. Okay, right. So back to what I was saying, that is okay, so yeah, so we have defined all these wires A, B, C in, sum, C out, wire 2, wire 3. All these are different wires. Now we are connecting them in different ways. So we have to make this gate XOR gate. We do this, that is assign this wire 1 is equal to A XOR B. Now look at this one. That is like wire 1 should be on this side, that is left hand side. A or B is right hand side. So what does it mean? You take A and do an XOR with B and assign this to wire 1. Okay, so these are the inputs and these are the outputs of the gate, like this logic gate. Then next one, wire 2, this wire 2, what is that? That's an AND gate, and basically wire 1 and C in, wire 1 and C in becomes wire 2, this wire. Okay, and the next one is like okay, okay, so here there's another way of doing it, that is always combo. Okay, so this is same as assign. Okay, there is no difference. Okay, always com means combinational always. Okay, always block. So it's same as assign, but there's not much difference. So what you do is like wire 3, this wire 3 is basically A and B. A and B. Okay, and you put it over there. Then we have sum is equal to this, and yeah, sum is equal to XOR of A and B. So this is the XOR operator, okay, and this is the AND operator, and this is the OR operator. So they create these logic gates. So that's the idea. And the C out is equal to Y2 or Y3. Okay, so type this out quickly. Okay, so ask, keep asking. Okay, please ask questions through Slido. Okay, don't ask questions over here in Zoom because it's distracting. Okay, so please ask it in Slido. I will answer from there. Right. So while you implement this, I will answer the questions I have in Slido. Right. So first one is like, is there a specific reason we use the 702 board? Okay. Oh, is it a generic selection? So 702 is like, I'm just using it because I have used it before. So you can use whatever board you have. So usually your own university, they will have a lot of FPGA boards. Okay. So for you to borrow and use. So that's how we are using, because the boards are expensive. So they cost around say 1 lakh or 80,000 or 1 lakh or something, some boards. So always borrow a board from the university. Then you can select that particular board. If it is a Xilinx board, you can select it over there in Vivado. Right. So I'm using 702 because I already have used 702. Okay. Then can we do the exact same project using Quartus? Of course you can, but you will have to use the Altera's FPGAs. So if you have an Altera FPGA, you can't use Vivado. You have to use Quartus, and you can do the same thing over there. But I will not be teaching how to use Quartus here, because the session is about Systemverilog, not about the software. Okay, right. Then in Quartus also you create a project the same way. You create a project. You can add the Systemverilog files the same way, add the sources, and you can do everything basically. So you can create an IP over there. You can do everything. Okay, why do we use always comb instead of assign? Okay, so is there a reason to use one over the other? Let's say. Yes. Okay, so there's a reason. I will let you know later. So that is like in the next oncoming slides, we will see that. If you are creating multiplexers, okay, so like we will create in the next ones. If you are creating those things, multiplexers and state, case statements, stuff like that, then you need an always com statement. So assign is like just one line, but inside always com you can put multiple lines. That's the idea. But they are both describing combinational circuits. Okay, so this, what I'm trying to say is this statement and these statements are equivalent. There's no difference between them in here. ISC and Vivado are same or not? No. ISC is like the oldest, say, incarnation of Vivado. So the idea is like, so ISC was the software of Xilinx few years ago. So for the older Xilinx FPGAs, I think I don't know, like Spartan or something. Yeah. So those older FPGAs, like you can't use with Vivado. So you need to have ISC. And nowadays ISC is like obsolete. So for the new FPGAs, nobody uses ISC anymore. And Vivado is much easier than ISC. Okay. So the reason for that is like, okay, I'm going to switch. You can look at the slides. Okay. Okay. So the reason for why Vivado is easy is, look at, if you look at this side, and you have all these what IP integrator, you have simulation, RT analysis, synthesis, implementation, and program and everything. So the whole thing, what the entire flow of FPGA design you have here. Okay, so you first create the sources, and then you do the simulation, then you do a synthesis, then you do implementation, that is place and route, then you put it in FPGA and then debug. So the whole thing is here. So in ISC, you have everything else, different options. So you have to go here and click there and like that, and it's kind of messy. So in Vivado, it's much easier than that. Okay, then back to here. Can we write the codes for wire 1 and 2 under the always com module? Of course you can. So wire 1 and 2, the same, like here you can do the same thing. So here you can say wire 1 equals A XOB, wire 2 equals this one, this one, this one. All you can do inside here. Okay. All right. So the reason I am doing this is, okay. So one thing to understand, I'm not teaching you how to write an optimal code. Okay. So like these designs are not optimal. So you're not going to take this and put it in somewhere else. Okay. So the purpose of this is I'm showing you the different features in the language. All right. So okay. So this and this are similar. So there are two different features of the language. So I am showing that they are similar in here. Okay. Right. And okay. So we have the um, okay. So there is this mm, okay. Yes, you have to create the file. Okay. And so the file is just a text file. You save it with the extension SV. Okay. SV is for Systemverilog. You save it with the extension SV, and you have to create a file. Yes. So you have to create it in either in VS Code. I created it here and saved it to SRC in here, and in there I'm typing this code. Okay. Or else you can create it in here as well. Okay. Right. So I'm going to disable this one because it's distracting. So use, let me check the link is working. ly/the interact. Okay, SV interactive. So to everyone, all right. So okay. Mm, mm, mm. Okay, so I will give like maybe 3 minutes to type this quickly. So I think a lot of people might have finished already, but if someone is lagging, like quickly type it in within 3 minutes. Okay, so somebody has asked, can you demonstrate creating the file through Vivado? Okay, so I will do this once. Okay, so let me do it again. Okay, so click this one over here. So that's add sources, add create design sources over here, and you can say press here and say create file. Already here, create file, and type Systemverilog, and you can put the file name as test file, test something. Choose the location in Systemverilog SRC like this. Okay, right. Okay, so that's how you create a file, and then when you say finish, the file will be created. And okay, so you don't have to do that, just say okay. over there. Then if you double click this test file, it will create all this, something like this. You can actually delete all this on this code is not needed. There is a what if you want, you can keep this. It's a comment, and over there you can type the code here. Okay, and you can save it here. The questions they've answered. Okay, so some quick questions. That is, okay, what is the difference between always at and always comp? Okay, right. So, okay, so always at is a is something similar, but it is from Verilog. Okay, the people who are familiar with Verilog have used always at for everything. Okay, so you can do the same thing in Systemverilog. Okay, because it's a superset. So whatever valid in Verilog is valid in Systemverilog. You can do that, but it's not recommended. Okay, so the problem with always is like it is prone to errors. So you don't know what exactly you are doing. So you do use the same always to make registers flip flops, to do combinational circuits, so for different purposes. So and sometimes if you don't put an else statement, I will talk about this later. When you put an else don't put an else statement, it will create latches, okay, which is bad. So there are like a lot of problems with always. So because of that, in Systemverilog, what they have done is they have removed all that. So it's still there. Instead of that, they have added some new things called always comb, always ff, and always latch, and we will look at those later. So the idea is like we use these things for particular purposes. Comb is used for combinational, ff is used for flip flops, for registers, latch is used for latches if you want. Okay, but latches are generally bad. If you want latch, you can use that. So that is the difference between always at. So in Systemverilog, you don't have to use always at all. So avoid it at if you can. Okay, but if you want, you can use it still. Do we need to keep indentations? Okay, so it's not necessary because Systemverilog is not like Python. So in Python, the indentations are important. Systemverilog here, as you see now, so Systemverilog works with this module end module. Okay, then these brackets and semicolons and everything. Okay, so even if you don't have any, if you put everything in one line, it will work. but it will be very hard to read. Okay, so don't do that. So Systemverilog is already hard to read, so don't make it even more harder. So like please use indentations. Okay, is logic a variable type? Can you explain it? Okay, so the idea is like it is not a variable in the sense of a variable in a say in a programming language. It's not like Python variable. So it's not like C variable. Okay, so logic is basically it is defining a wire in here. So that is the loose definition. I will give the exact definition when I talk about data types later. Okay, so there are like wire types and what var types, then like 4-bit types, 2-bit types, and there are like many things later. I'll talk about them what over there. If you want, you can check the slides. Okay, like if you go down, you can see there's a slide called data types. Over there, I have mentioned those. Okay, always attend the same. Can I run existing Verilog code with an SV? Of course. So you can run the existing Verilog code with an SV extension. You can do that. Yes. Then how to add the code to Vivado project? I think you have seen already. Yeah. What are the extensions you need to install VS Code? Okay. So for now, you don't need any extensions right now. But if you want to make your life easier, you can use something called. Okay, I have installed something in here that is called. Okay, this one. But setting this up is a bit difficult. Okay, you have to use something called the Verilator, and like it's a bit difficult. But if you want, you can try that. Okay, so BlueSpec Systemverilog this file. So it helps to find some errors in the code, but it's not very helpful. Okay, like because it's this nobody uses this language much. So like say Python, there are like thousands of people using it. So there's a very good Python extension. And what Verilog, only few people use it. So because of that, there are no good extensions for this. Okay. Now, yes, if you are using VS Code, you have to save it in SV. Okay, and save it inside the SRC folder. All right. What are the extensions we need to install on VS Code? Okay, answered that. Done. Okay. So I think you have implemented this. You have written the code. Make sure there are no spelling mistakes, typos, everything. Okay. So now we are going to put this in there and do the, okay. Then we are going to write the test bench. Okay, before that. Right. So now the next one, what we are going to do is, what we did here is RTL design. That is, we have described the circuit. Next one, what we are going to do is, we are going to do a test bench. So test bench is what? It is non-synthesizable. Okay, so you can't put that in a chip. Okay, it's non-synthesizable. But okay, it's not synthesizable, but we will be using it to create a module using which we will be verifying the behavior of the RTL. Okay, so the idea is like it's something like this. Okay, now look at this. Our test bench program is we put this around our RTL module. Okay, we have the RTL module. We put this test bench program around it. From our test bench program, we give the inputs at certain clock cycles or certain times. Certain times we give the input. Then we get the output from the RTL, and we see it in a diagram or something whether they are correct. Okay, so that's what we are doing here. So this test bench program is not synthesizable again, and we use constructs like this. So if display is to print it in the screen, if open, I'll show everything. If open is to open a file, you can't put this on a chip again, right? And the idea is like there will be different initial blocks, initial begin, initial end, initial like that. So initial begin and end, and you can put multiple initial blocks inside a test bench. All these initial blocks will be running in parallel. They will start in parallel and run in parallel. Okay, so if you want to, I will show you that also. Then okay, so what's where do you put this test bench? You can simulate this test bench with okay, any simulation software. So one is QSim, is used by Quartus. Model Sim is like a very popular one. Then Vivado simulator is used inside Vivado. So we'll be using this one. Okay. And using these simulators, you can display the waveforms clock by clock. You can see what happens in every clock cycle. Then you can input a file and output a file for complex operations, right? So how do you do a simulation? Okay, so I'm going to show this, but if you miss that, come back to this video and see. Okay, so this is how you do a simulation. And like when you do a simulation, you will find a lot of bugs. So like if you made any typos or any mistakes, it will show up. So how to fix those? So if you have any like later on, you can come back to this video and see that. Okay. So all right. So this is the test bench. Okay. Right. Now what you do? Look at this carefully. You have to create a new file. Okay. So create a new file called full ladder TB. Let me create that in VS Code first. And okay. So if I'm going to create this, I create new file and I save the file as full adder tb.sv. Okay. And I save it in src folder, the same folder, src folder, full ladder TB. TB is for test bench. Save it over there. Then over there, module full ladder TB, you have to type the code. Okay. In module. Right. So and save it. Okay. So once you save like that, you can add it into the project. Okay. So if you create it outside using what VS Code or something, you can add it. Add or create design sources. Sorry, go back. Add or create simulation sources. We are going to add the test bench. So it's a simulation source over there. Add the file, this TB file. Add it over there like that. Okay. Then say finish. Okay. Okay. Now where is it? It is under simulation source. Okay, not under design source, under simulation source. If you open the sim1, you will see a TB. Okay, this TB file. You can double click it and it opens here. If you want, you can create the file in Vivado as well. For that, you say press new simulation source, create a file. Okay, create a file, Systemverilog, file name, say testdb. In this case, it's full ladder TB. Okay, type full ladder TB here. TB dot okay TB, not local to project. Don't select this. You have to select the location. Location src. Okay, src. Then okay, the file already exists because I just created it. Then I'll put a different name, testdb, and create it over there. Right. So it's created and finish. So this is okay. Just give okay. STB, double click this, it opens here. Okay, and in here you type that code. Okay, from the slides. All right. So for the experienced people, like I'm taking some time with the first example because like there are like a lot of people, 163 people inside. So if they don't get the first example right, like they will find it difficult for the next ones. Okay, so this ones I'm doing slowly, and so everyone what get familiarized with this one, because for the next examples I'm not going to show this one by one. You have to do it by yourself. Okay, so type this code. I will give say 10 minutes. Okay, and meanwhile you can ask questions. Okay. So somebody has asked like, can first two assign statements interchanged if there is no any execution order? So he's talking about this one where you have the different assign statements and where you can you interchange it or not? Of course, you can interchange it. So yes. So here there is no execution order from the top to bottom. Okay. But usually we put the declarations before the assign statement. So you have to put logic via one before you say assign via one. After that, you can put in whatever order you want. It doesn't matter. Okay. So you can do that. Can you explain the difference between Verilog code and Systemverilog code? Yes. So Verilog code, it looks similar. You have the module, you have this one. Instead of logic, you have wire, you have reg, and all these things. It looks kind of similar, but like it is a older language. Okay, so like it was before 2000, like 1995 to 2002, like that. It's an older language, and Systemverilog is improved, so it has like more features and everything. So I'm not introducing both Systemverilog and Verilog here because it'll be confusing for the newcomers. Okay, so if you already know Verilog, just look at this and okay, so this is the way we do in Systemverilog. Okay, so the same things which you know in Verilog, this is how we do it in Systemverilog. And in some of the slides, I will give some examples of like comparing between both. Okay, but I will not talk about it a lot because it will be confusing for new people. Okay, right. Okay, why are there two columns in the slides? So that is in a test bench slide. Why is there two columns? Because I can't put everything in one column. Okay, so if I put it horizontally, you'll have to turn the screen to read it. So just for the space, I have done like this. But when you type the code, you type it at once. Okay, so you start from here, you type all this, then you type this, everything in one file, right? Okay. Can we use the same software to create RTL design for Altera FPGAs? No, you can't. Okay. For Altera FPGAs, you have to use Quartus, not like Vivado. Okay. But the same things you can do in Quartus, but the controls will be different. Okay. So okay, somebody has a problem with the proxy. Yeah, I will look at it after the lecture. Okay. So send me an email and remind me. Okay, you type it from the slides. I will copy this into. So I'm going to copy from the existing code I have. Okay, and I'm going to create the same module so I can show you how to do these things. Ladder. Okay, so it will give you time until 11:40 to type this. Okay, so somebody has asked like, can you explain the test bench code? Okay, I'm going to explain like, okay, once I run it, and okay, once I run it, I'll show you what happens in every line. Okay, and how this RTL code can implement circuit on chip. So this is not RTL. This is test bench simulation. What we did before was RTL. Okay, so how is it implemented on chip? Okay, so what we do is like, in the RTL, we are telling the synthesis tool how to create the circuit. Okay, so we tell, okay, what are the inputs, what are the outputs, and how they are combined, the AND gates, OR gates, and everything. We are telling those things. Then the synthesis tool, we will look at it later. When you do synthesis, it will create that, it will convert that into actual logic gates, or else in FPGA into LUTs, lookup tables, and flip flops and everything. We'll look at that. Okay. Vivado is only for Xilinx FPGAs. Yes, Vivado is only for FPGA Xilinx. Okay, somebody has a proxy problem, but he says it works in Ubuntu. Okay, then I don't think there are legal issues, because this is okay. So there are no, I don't think there are legal issues, because Vivado is free. For like most of the FPGAs, it's free, so that's fine. And they have like a lot of tutorials as well. You can check them out. So how to use Vivado for different things. Then Systemverilog giving instructions for operations using okay. So I'll be talking about that later. I'll be showing that add operations. Yes. So somebody's asking this one. I'll show that right now. Wait. Can you explain what a test bench is again? Yes. So test bench is basically a module we write, like a virtual module. So the person who asked the question, you look at here, other people type. So A test bench is a module we build around the RTL module. Okay, so the actual circuit. It's a module we build around the actual circuit, and the test bench is not synthesizable. Okay, it is just there to give signals and get signals and test it in simulation. The RTL is the actual module, actual digital circuit, which we are building. Okay, so that's a difference. Are test bench code executed line by line? That's a very good question. Okay, which I'll show you in a moment. Okay, then can you show how to run the code? Why did you skip the IO port selection? Yeah, you can create the when creating the file through Vivado. Yes, you can do that. So you can create the IO ports and everything through Vivado, but I personally prefer to do it by hand. That's like typing the code. Okay, so if you want, you can do it like that as well. All right, so let's move on. I think you have typed, everybody has typed. Okay, so there's one person who asked, okay, why we are typing this code? Like, so he asked through WhatsApp, why are we typing this code? Why can't you copy and paste from GitHub? So the reason is like at every point in here. Okay, now look at this code. At every line in the code, we are doing different things. Okay, so like I'm going to explain like why what we are doing at every line. Okay, so and these are the features of the language. Okay, so if you just copy and paste on the code from there, then you don't get to use the features. Okay, you don't get to think what happens in every line. So that's a general idea. But later on, if the code doesn't work, you can later on copy and paste from GitHub. Okay, so this is to give you some hands-on experience. All right. Now, okay, so before you simulate this, before you run this code, I will explain what happens. Okay, so yeah, so pay attention. What we have is it's a test bench. Okay, so it's a test bench. It is around the RTL, right? So we define the test bench as a module. It's a module, test bench, in module, and it doesn't have any ports. Okay, so that's an important part. Why? Because we are not connecting the test bench to anything else. So test bench is like a fully self-contained thing, and inside that we are giving the signal, we are creating and giving the signals. Okay, because it's not synthesizable. Okay, so yeah, so it doesn't have any ports. It's an empty, like the port declaration is empty. So we are not telling input, output, or anything, right? First, we say the time units. Okay, so when we are doing simulation, especially in waveform or like in simulation or anything, we have to tell the time unit and time precision. So time unit means what? Time unit means whenever I say this, say here I am telling, okay, so here I am telling hash clock period into 2. Okay, which means I'm giving a delay. I'm asking it to wait for this time, this much of time. So clock period is what? Is 10. So I'm asking it for 20. So 20 what? What is a unit? The unit is this time unit. Okay, so we are declaring the time unit here. So afterwards we can say like hash 5, hash 10, okay, things like that. Okay, so it's 1 nanosecond. So which means this delay will be 10 into is 20 nanoseconds. Okay, this delay. Okay, all right. So time precision. So time precision is, it's not very important, but the idea is like the simulation tool, it does simulation in discrete time steps. Okay, so we are telling like we need a time precision of 1 ps. Okay, so that is like 1,000th of a nanosecond, I think. Yeah, yes, so we need that precision. So you can, these are like default values, you can just use this one, it doesn't matter. And by changing this, the simulation doesn't run fast or slow or anything. Okay, so because the simulators are optimized, they do the simulation only at particular points. They don't do it for every picosecond. That will take too long. Okay, they just run the code until something happens, then simulate that, then simulate the next event, like that. Okay, so right, so now this is a local param. So local param is a parameter. So what are parameters? Parameters are constants. Okay, you can either say parameter means you are giving something from outside. Local param means it's a parameter you are defining inside, only for the inside purpose, and it's a constant. So we are declaring this at 10, clock period as 10. 10 what? 10 nanoseconds, because the time unit is 1 nanosecond. Okay. Then logic clock, like we are declaring the logic clock, this one. Okay. Now this, it is not an input or output. Why? We are going to create the clock signal here. Okay. Look at this. We are creating the clock signal here. We are not giving the clock from outside because this is the test bench. Okay. So in the test bench, you create the clock signal, you give it to the circuit. Okay. So how do you create a clock signal? So we declare the logic here, then see inside an initial block, initial, begin and end, we say clock equals 0. What does this mean? This means at the very beginning, clock is 0. When the simulation starts, clock is 0. Afterwards, we say forever at clock period by 2, clock is equal to not clock. So that means at every, okay. So when we run this, we are going to get this, something like this. Okay, I'll show you. We are going to get something like this. But what happens is this. At the very beginning, clock is 0. Okay. And afterwards, at every 5 seconds, at every 5 nanoseconds, this becomes what? See, after 5 nanoseconds, over here, clock becomes 1. Why? Clock goes to not clock. So basically, what initially it was 0, now it becomes 1 after 5. Then after, in the next 5, 10, it becomes 0 again. Then 15, it becomes 1, becomes 0 again. So the clock signal is alternating between 0 and 1 every half a period. Okay, so at a one full period, you have like a full clock signal, clock cycle. Okay, so the clock cycle is 10 nanoseconds. Can you see here? Okay, so this is how we generate a clock signal. All right, so this whole part of this code, okay, this code is just to generate the clock, and we will use this piece of code in every test bench. Okay, to for clock generation, right? So now, right, then after that, after generating the clock, we are doing some other things. That is, we are going to define some more signals. That is logic A, logic B, and C in, and this one. Okay. Now look at this. These A, B, C in, sum, and C out. All these things are again different wires. Okay. What are we doing? We are giving this the RTL module. Okay. So your RTL module is this one, right? Full ladder. The RTL module has inputs A, B, C in, outputs sum and C out. Okay. What we are doing is, in the test bench is around this RTL. In the test bench, we are going to create wires A, B, C in. We are going to connect the A, B, C in to these wires. And the output wires, the sum and C out, we are going to connect it to the wires we create over there. Okay. And now look at this carefully. If you give the same name of these wires, the input wires A, B, C in, to the wires you are creating outside, if you give the same name, then you can instantiate it. You can like connect them very easily, okay, using a shorthand. All right. So the shorthand is this one. This is called a module instantiation. Okay, that is, I'm creating a full adder module. We defined the full adder module before. We are creating a full adder module, and I give it a name for that module, FA. Okay, and in that FA module, what does this mean? Now, this is a feature of Systemverilog. It's not there in Verilog. So this feature is what it's called a wildcard instantiation. Okay, that says you can any ports that have the same name as these wires, same name and same type and everything, they will get automatically connected to these. Okay, so which means in the FA we had something called CLK, the clock, that gets connected to this one. Okay, so we take that. Okay, say, so this is the full ladder module. Okay, I'm instantiating it here. This A gets connected to this A, this B, the input port B connected to logic B, the input port C in from this module. From inside this module, it gets connected to this C in. The output of this module, the FA has an output that is sum. That wire is connected to this wire, the logic sum. And the output wire C out is connected to this C out. Okay, all these wires are connected to these wires with the same name. All right, and that's called a module instantiation. Okay, wildcard instantiation. You can also do it the hard way. So this is the easy way. If you want to do it the hard way, you have to do something like this. Full adder. I'm instantiating this. Okay, so you can't see that. Okay, maybe now you can see it. Okay, full adder FA. So inside here, I can say dot CLK. The clock input of this module. I'm connecting it to this wire, clock wire, CLK, comma, dot A. I'm connecting the A input of this one. From here, A input, I'm connecting it to this one. Dot B, dot C in, dot sum, dot C out, okay, and you can this. Okay, so like if you put everything in one line, it's hard to read, so we usually do something like this. Okay, right. So now this and this are same. Okay, so instead of writing all these signals one by one again and again, so like you connect clock to clock, you can connect A to A, connect B to B, C into C in. Instead of doing all this, you simply do this. Okay, and it will automatically connect there. Now, what is this? These are comments. Okay, comment means like the tool will ignore them, right? So once you do that, okay. So now you have connected the wires, module instantiation. Then after that, what happens is, in the initial begin, we are going to give the signals one by one. Now see what happens. Somebody asks whether the code is running sequentially in here. Yes. So what's happening is, there are two initial blocks. Can you see that? Initial begin here and initial begin here. These two initial blocks are running parallelly in the same time. Okay. So here you can see the clock generation happens all the time in parallel. While we generate the clock, over here, we are changing A and B at different times. Okay, so that happens here. I will go through it one by one. Both are happening in the same time. Okay, we are changing A and B while we are changing clock also. So this block and this block, they are running in the same time, parallel. But this block is running, like inside this block, you are running this line first, this line first, this line first, this line first, line by line, this code is running. So that is how test bench works. Okay, all the initial blocks are running in parallel, and all the inside the initial block, the codes are going line by line. The code is running line by line. Okay, now what happens here? See, okay, look at this carefully. At 0 over here, okay, we are telling okay, so this at postage clock, not here. Actually, it should be here. I made a mistake. Right. So, right. So this 0 corresponds to this line in the waveform. Okay, at this postage, I'm asking it to wait for 3 clock cycles. Okay, there is give a delay of 3 clock cycles. So what happens? You have 1 clock cycle, you have 2 clock cycle, you have 3 clock cycles. Then we come to the next postage after 3 clock cycles. Okay, in here. All right. Now within this time, can you see these lines are red color? Yeah, the B and sum are red color. Why? Because for B, we haven't given any value. We haven't given any initial value. The value you give here, A equals 0, is not the it's not the entire value. Okay, so it is the initial value. At the very beginning, what is the value of A? So at the beginning, A is 0. But B, I haven't given an initial value. So as a result, it is a unassigned wire. Okay. So then the like the value that A gets, B gets is X. So X means undefined. So if you connect a wire, like if what you get these red lines when you try to assign two things to the same wire, or else sometimes if you don't assign anything to the wire, okay, then you will get these red lines. Okay, so that is an advantage of using this logic. So like logic is a, I'll explain it later. Logic is a four type. So four state type. That means the logic values A can take four values. It can take 0, it can take 1, it can take X, it can take Z. Okay, so Z means high impedance. That means if you don't connect the wire anywhere, okay, like inside the RTL module, if you just leave a wire hanging, then it has a high impedance. So or else X means undefined. Okay, it doesn't know what value to give. Okay, so then it has four types. The A wire can take four values. Then the advantage of using logic is, then there is another one called bit wire, bit type. If you use bit, it has only two values. It can take only two values, either zeros or ones. The advantage of using logic is you can find your mistakes in your RTL design or anything very easily. So inside the RTL code, if you don't connect a wire somewhere, if you make a mistake, if you just leave a wire hanging, you will get a blue line here. Or if you make a mistake and assign two things to the same wire, you will get a red line here. But if you put a bit, you won't get that. You will get either 0 or 1, and it will look like a valid value. Okay, so that, which is why we use logic. Okay, I'll talk about it in detail in the data types slide. All right, so after 3 clock cycles, we have come to this point. Okay, from here to 1. At 1, okay, at passage clock. So this is a positive edge. At this positive edge, what are we doing? We are giving A 0, B 0, C in 0. Now, can you see all these three lines happen at the same time? Okay, so at this same time, we are giving A equals 0. A was already 0. We are again giving A equals 0. We give B equals 0. B was undefined previously. We are giving B equals 0. C in equals 0. C in was undefined previously. We are giving C in equals 0. All right. So we give that all this in the same time at this passage. And then we say another passage. So now this goes to the next passage. Okay. What happens at next passage? At next passage, we are giving, okay. So when you give these inputs, what happens? When you give, okay, at the very beginning, so forget about this, at the very beginning, passage clock, at here, okay, A is what? A is 1, B is undefined. Then C in gets calculated. The RTL module is doing this calculation. Okay, the RTL module is taking A and B and it is doing what? Now look at this. This is the lookup table. Sorry, this is the truth table. This is the truth table of a full ladder, 1-bit full ladder. Okay, and if A and B are 1 and undefined, then the sum is calculated as undefined, because sum, to calculate the sum you need B. So the B is not there, so sum is also undefined. Okay, but to find the C in, you don't need B. So C in is already calculated as a 0. Right. Now at this clock cycle, we are giving what? A and B 1, 1, 1, and for C in also we are giving 0, 0, and 0. For A, B, C, we are giving 0, 0, 0. That means for A we give 0, B gives we give 0, C in we give 0. As a result, we get sum equals 0, C out is equal to 0. Okay, sum here is 0, C out is 0, which means the circuit is working for this particular case. Okay, so now we give a different case and see whether the circuit is working. Now at the next passage, we give A equals what? A equals 0, B equals 0, C in is equal to 1. That is this case, A 0, 0, 1. When you give that, you give sum equals what? Sum equals 1 and C out equals 0. Okay. Now third one over here, that is after 2 clock cycles. Okay. So I'm giving a delay of 2 clock cycles. Then I give a passage clock. At the next passage clock, I'm giving 1, 1, 0. 1, 1, 0. ABC in 110, that corresponds to 110 here. The result should be 0 and 1. Okay, sum should be 0, C out is 1. Sum is 0, C out is 1. 3. Next clock cycle is here 111. Output is 11. Okay, so 111 we give it here. Output is 11. All right. So that is the 1-bit full adder test bench. All right. So let me run this let me do the simulation and show you. Okay. So now look at this. I have okay. So I have this file and I have this file, the full adder module as well as full adder TB. I'm going to add these to, I think they already added. Yeah, they already added. We added them to Vivado. Okay. So when you add something to Vivado and if you edit the file outside, it will say the file has been changed and it will ask you to reload. And you click that and it will reload the file. Okay. Okay. Or else you can close it and open it again. Okay. And you get the file with all the changes. Okay. Right. So, right. So once you do it, now can you see here that, all right. One person has asked, the full adder is inside TB. Is it okay? Yes, it is supposed to be inside TB because like a TB test bench is a module that wraps around your RTL. Okay. And that is under simulation sources. You can see in the design source, RTL source, the TB file is not there because it's not synthesizable. Okay. The TB module is not there. But in the simulation source, TB module is there. Inside TB, full adder module is there. Okay. Now, before we run the simulation, I will show you something quickly. What if we make some syntax errors? Okay. So I'm going to remove this semicolon. I'm going to remove this semicolon. I'm going to remove this end module. Okay. And I'm going to replace this with this end. I'm going to replace with end letter. Okay. And say something like for assign, I make a spelling mistake, let's say. Okay. So sign. Okay. So I have made a lot of spelling mistakes and errors. Okay. Right. Now, if I do this, now what happens? Now it says there are syntax errors in here. So then it will not recognize the module as a module. And if you go into design source, there is no design source. Okay. Right. So then you can go into here and see that, and you can see these syntax errors in here as well. That is, down here, go to messages. In the messages, remove this info. That's mostly useless. Remove that. Right. So now you can see the syntax errors over there, and you can see the syntax errors here as well. Okay, it underlines the errors, but it doesn't underline everything. We'll see why. Okay, on this side, you can see at which lines you have the errors. Okay, right. So first one, it says there's an error in this line. Okay, so what is the error? Logic, this one, this one, this one. Okay, there's no semicolon. I put a semicolon and I save it. Now look at this. Look at this carefully. I have put the semicolon. I have saved the file. It says again there's an error. In which line? In the same line. Okay. So what? Okay. So where's the error? Logic y1, y2, y3 semicolon. This is right. There's no mistake in here. Then where's the error? The error is on the line before this. Okay. So this is a kind of a headache with Verilog as well as Vivado. Sometimes it gives the error in the other line, in the next line. Okay. So if it says there's an error in this line, you always look at the line before and the line next as well. Don't look at only that line. So this line is perfect. There's no problem. But in the previous line, we are missing a semicolon. You change that and this error goes out. Okay. Right. Then there is an error over here. What does this say? This gives us in 20, SV20. Okay. Syntax error near end. Near this end, there's a mistake. What's it? Okay. There is no end. It's not Python. This is Systemverilog. So we use end. And then we say, again, we have an error that is over. Okay. So on the last line, there is an error. Okay. What is the error? Like the line is, okay. Now the line looks perfect. There's no problem. But it says an error. File ended before the end of clause. Okay. So this means it is missing something over there. What is it missing? We haven't written the module should end with end module. Okay. Right. So if you do that, that will disappear. Okay. Now there is an error here. All right. The sign should be ASSIN, but it doesn't show the error. Okay. Now, so some of the errors you can't catch it this way, like this. But when I simulate, it will give the error. Okay. Okay. How do you simulate this? To simulate this, look at this carefully. In now design sources, you have the full ladder here. Simulation sources, you have the full ladder TB here. Okay. So in the full ladder TB, if you want to simulate this one, you have to right click this and make it as set it as top. Now it is already the top module. So let's say I have made this as top. Okay. So, okay. So now if this is not the top module, so if I simulate it now, it will simulate the test file. Okay. If I want to simulate full ladder TB, I have to right click this and click set as top. So all these things I have put it in the videos. So in the slides. So like how to do a simulation with what Vivado. So I have told like how to set the top modules and everything. Right. And after doing that, now I'm going to simulate this one. I click run simulation. Run behavioral simulation. Okay. There's an error. All right. There's an error. Now what is the error? We know what is the error, but let's see how to find it. Okay. So first one is like it is showing here. Okay. It is putting what it's highlighting and showing the errors here. In addition to that, like if you want the full details of the error, what you have to do is it doesn't show here. See, okay, sometimes it gives the error here. Assign is an unknown type. Okay, it has given the error here. But if you want more details, you have to open this particular file. This particular file, elaborate.block. Let's see how to open that. That gives the entire error. Okay, so for that, go into your text editor or something. Over there, open. Go into projects. So the path is given here. See, projects, project 1, sim1, behave, xsim, inside elaborate log. And there is something called the xlog also. This one, xvlog. These two are the log files that give the errors. So it gives like a full description of error and this one. So for an example, if I open this, in the elaborate file, you have a like a full adder.sv. On the 23rd line, there's an error. And this one is fine. Xlog is fine. So what's the difference between xlog and elaborate? Xlog is basically the simulation. So first, the like it runs kind of a syntax test. There's no problem. Elaborate is where like it creates the like it reads your Verilog code and converts it into something low level. That's called elaboration. So or else like it opens up the loops and everything. And in there, like you have an error. Assign is of an unknown type in 23rd line. Okay. So what is the 23rd line? 23rd line here. So that's an error. ASSIGN. Okay. So if you have errors, that's how you do it. Now see, even after fixing the error, this doesn't go away. Okay. So to make it go away, just click delete. Okay. And even then it doesn't go away because we have to run the simulation again. Okay. I think we are few minutes over the schedule. Okay. We are done here. Okay. So then you get the waveform. Okay, this waveform, you press this button, zoom fit. Okay, and you can yeah, then you can zoom in and out using press the control key, and you can use the mouse scroll wheel. Okay, zoom in and out, and you can even click a particular line, and you can press the right key, you can go step by step. For an example, I can go half clock cycle every time like this using the arrow keys. Okay, and you can see what happens here. Okay, right, and I will tell you some more details like how to change the colors and everything in the other example. Okay, so like you can do that and check the results. Okay, so we have done the first simulation, and yeah, okay, and we ran out of time before we do the next one. Okay, so we will do this one in the next class. Okay, in the next session. All right, so with that we will finish this session. So it's 12:15 now. Let's finish this session. Yeah, so thank you everybody. Now thing is, your feedback matters. All right, so we need your feedback. Please go to this link where I have been asking questions. Okay, so go to the link here, over here, and go to Pulse, in Pulse, and in feedback you type your answer. Okay, and press send. All right, so tell about like whether you like the session or not. Was I too fast? Was I too slow? Do I speak too fast? Okay, or else you can't see the screen, or like okay, those things. Other than that, you tell, okay, like whether you like this method, like are these examples too hard or the examples too simple? Okay, or how can we improve? Okay, so can we change something? You tell about this, everybody. Okay, go there and give your feedback. This one. And the next session will be at 7 p.m. today, the second session. Okay, the Zoom link is here. Okay, and the Zoom link is there in your registration page as well. Okay, and for the code, you can go to github.com and get this. From here you can get the code. Okay, and that's like a working code. So if you have any problems, you go there and get the code and check it. All right, and so if you had any problems, like check them before you come the next one. I will answer the questions which I get in this one, so others can leave. Okay, what is the logic keyword in these codes? Is it a variable type? Okay, that was it an old question? It's a new question. Okay, so logic is, again, logic means a wire. Okay, either it's a wire or a register. Okay, so we will see like how to create registers later. So logic means just a wire. Okay, why is it used this particular key? What this? Okay, so this is called a blocking operator, blocking assignment. No, this is called a non-blocking assignment. The idea is like at every passage clock, then okay, so because we are doing something at this time, if you put equal, okay, so how do I explain this? You can actually put equal here without this, but that can give some errors later. All right, so this operator, this is used because we want to assign something to A after this passage clock. Okay, so that is at this passage clock, at this particular passage clock. Okay, after a small moment after the passage clock, we are applying this to A. All right, so that is how things happen in actual circuits. Okay, so actual circuit, right at the passage, nothing happens. Okay, so you see the passage, after a very small delay, something happens. Okay, so if you want to get that kind of a behavior, you have to always give A this equal to 0. So that's like a kind of a rule of thumb. We always use this one in test benches. Okay, but over here there are no like edge sensitive things, so we are just saying A equals 0 at the very beginning. Okay, then difference between equal and this one. Okay, this I will talk about it in the next session. When is the next session? At 7 p.m. today. Okay, yes, Systemverilog is okay. I think I answered the question before. Okay, without using always comb, can we just use assign? You can use assign only if, like, if it is one line. Okay, so like if your assignment is one line, If you want to put a multiplexer, okay, it is very difficult to do it with the sign. You can still do it, but it's quite difficult. So other than that, we will use like always comb. You will see it in the next examples. Okay. It's fine. And okay, what is the function of forever? So forever is basically it's telling you to do this again and again, like keep doing it. Okay. So this is like an infinite loop. Okay. So forever at every like after, okay, so you give a delay of clock period by 2, then you change the clock into, you toggle the clock. Okay. Then after that you come back and again give a clock period by 2, then you toggle it, and like you keep on doing it again and again forever. Okay, that's the idea. Then does touch bench execute parallelly? I answered that. And dot a means the input in the adder, and a means yes, very good. Okay, so that is like dot a means, that is like he's talking about this one. Okay, so dot a means the input, a means the wire we have it in the test bench. Okay, this wire. Dot a is the input of the RTL module. Okay, right. If they have the same name, you just do this. Okay, right. Okay. Can you show again how to run the simulation? All right. So you can go to the, like in the same slides, you can go here. Okay. So go back. Okay. So there is a Vivado simulation. This video is there. It shows you how to run the simulation. Okay. And this video shows you how to fix the syntax bugs. Okay. So similar bugs, how to do that and everything. So look at those. Then can you upload the video before next session? Okay, I will upload it now. Then can we assign values to negative edge of the clock? Okay, I will upload it now and send you a link. Okay. Yes, you can use the neg edge as well. Okay. So instead of posage, we can say neg edge, but we usually do things in the posage, and we usually don't mix both posage and neg edge. Okay. So in there are certain cases where we mix both. For an example, DDR. So DDR is the RAM. It works in both edges. Okay. So okay. So we can, there are things like that, but when we design stuff, usually we don't mix both because it leads to confusion as well as some other problems. So we use only posage, but you can do it, of course. When is the next session? It's at 7 p.m. today. And when is the third session? Third session is at 8:30 tomorrow. Okay. So I have I'll send you I have changed the time. I will let you know. The third session is tomorrow night. Then we have the recording? Yes, you can. Is FA a keyword? FA is not a keyword. FA is the name of the module we are making. Okay. So full adder is the type. So like we have created a module called we have created a circuit. Now the idea is like you can create multiple circuits with the same module instantiation. Okay. That means you have the full adder module you have written before. You can create FA1, FA2, FA3, FA4 like that, or else you can put some other name. You can create 4 or 5 full adders inside if you want. Okay, so that's why. So this is a name we give it to this particular instantiation. Okay, and that is the type of the module. It's a full adder. Okay, so you can create multiple copies of the same digital circuit you created using that way. So FA is not a keyword. It's just a name we give. Do we have to save the waveform before we exit? No, you don't have to. If you want, you can save it and keep it, or else we don't need it anymore. There is no clock input to the full adder module, but clock is there in the test bench file. Wait, what? Yes. Yes. So full adder module doesn't have a clock. Yes. Okay. Reason is full adder is a combinational circuit. Okay. So combinational circuit means it has just gates. So you have a gate and you do something and give an output. there are no registers, there are no flip-flops. So you don't need a clock for this. Okay. So the full ladder module doesn't have a clock. I think I made a small mistake when telling that. Over here, did I? Yes. Yes. Okay. So this is a mistake. There is no clock. Okay. Full ladder has only A, B, C in and these things. Right. So it doesn't have a clock. Yeah. But the clock is in test bench. Is it a problem? No, it's not a problem, because we need a clock, because at different passages only we are giving these values. So that's why I'm using the clock here. But you don't need the clock for the for the RTL. This particular RTL module is combination, so there's no clock. So that's completely fine. So the idea is like at different times I'm giving different values. Okay. Okay, I have installed VS Code now. It doesn't show the colors. So you have to save the file as a SV file, Systemverilog file, to show the colors. Okay. There is no clock input to full ladder module. Yes, I answered that. And if full ladder module like a class, if it is an instance of the full ladder class. Yes, kind of. Okay. So, but don't think of it in that way. So it's you are right. So it's something like that. So full ladder is like a class, and full ladder, this one is like an object. But don't think of it that way, because don't confuse the programming constructs and the HDL constructs, because HDL is not a programming language. Okay. Because if you think like that, then there will be a question. Okay, if full ladder is a class, can classes have methods? Can they have functions and everything? No, they can't, because it's a circuit. Okay, like a circuit, you can't put a method inside a circuit. Okay. So now those things don't translate. So the idea is kind of similar, but don't think of it as a class and object. Okay. There are classes in Systemverilog. So Systemverilog is an OOP language. There are classes, there are objects and everything. We will talk about it later in the last example, maybe in the next few examples. But like this is not a class. Okay. Right. So the other question I'll answer next. Okay. So you guys can go now. Okay. Thank you so much. And I'm sorry for the delay, like for the question and answers. Yeah, I will upload this to the. Okay, I will upload this and I will share you the link through email. Okay. Yeah. Thank you.